All right, hello everybody. So today we are going to start thinking about extending our models beyond our sort of linear assumptions. So beyond linearity. And so most of what we've talked about has been focused on linear models. And for good reason that these are very popular. But as we move away from linear models, we start to lose interpretability. But the benefit of that is that we gain in predictive power. Ooh. Predictive power and flexibility in fitting models. Okay, so what does this mean? As you can probably imagine, in our linear regressions where we're fitting some line through this data, some straight line through all of this data, we have these general equations, right, that describe the fit of this line. And we have these betas to describe the slope, or in other words, the effect of what happens to our outcome as we have changes to X or our inputs. So it's pretty straightforward. And at this point, we should be pretty comfortable with interpreting those. But let's suppose I start to get a little bit more complex. You can imagine that the functional form of this no longer translates to the simplicity that we have in a linear model where you just have this like one coefficient that describes the effect. We don't really have an equivalent of that once you're, drawing these squiggly lines, right? But one of the things that you are able to do is basically fit data that's not linear. And if you think about the world of data in general and thinking about trends, actually, there's not too many things that are truly linear. And a lot of the reason why we employ the linear regression and similar types of models is specifically because of the interpretability aspect. And so that trade-off is worth it to lots of different types of analyses. But it's also important to think about some of the shortcomings of assuming linear fits. And so we're going to start to stray away from that now. So some examples of nonlinear fits that we're going to slowly walk through. So we've got polynomial regression. We have step functions, regression splines. We have smoothing splines. Local regression. And general additive models. So we'll be looking at these a little bit more in detail, starting with these, thinking about sort of more basic functions. And these are really families of functions or transformations that you can apply to specific variables. Okay, so the first one to start with is the polynomial. And so that is where I take something that looks like this, our standard or typical linear regression, and we transform it to include polynomial terms of my input variable. And so if you recall, we did actually look at an example of this in the past, but we're going to kind of more generalize it, standardize it. Okay, so essentially by sort of adding these polynomial terms, you're introducing additional flexibility into the model. So the way that I might think of this qualitatively is we're turning our straight line into like a slightly more squiggly line. And the more polynomial terms that you have, the more sort of wiggle room, like literal wiggle room that you have to introduce that squiggliness into your line. This can, however, become overly flexible. And the sheer nature of these polynomials is that oftentimes they take on a strange shape near boundaries of X. Okay, and so let's go ahead and go to our code and see if we can implement some examples of a polynomial. So I will go ahead and jump on over into RStudio. And we're going to do something similar to the start of our class, where we define a true function. But this is going to be slightly different. We're going to have our deviation or our error term. So this stuff is similar so far, but now instead of, I believe what we had before was we defined y as like half of x plus the deviation. We're going to do this like extremely non-linear term here. Okay. Oop, hang on. So let's take a quick look at this plot. So you can see this is a fairly nonlinear pattern as it relates x to y. And if we ran a simple linear model, we can see what this looks like. You see that we have this 0.5 coefficient, which actually extracts the linear term here, but the rest of it is omitted, or the rest of the sort of variation. And in fact, if I were to include that fit line here, you would see the line generally goes through, right, the average trend of all of these points, but it does not capture the sort of fundamental nonlinearity, which we know as part of our true function, right? That sine x times cosine 10x term. So instead, what we can do here is we can include a polynomial in order to introduce the nonlinearity or try and capture the nonlinearity. So the way we use that is a function called poly, and that will give all of the polynomial terms. In fact, we can take a look at what that looks like. If I just do, let's say, 4 polynomial terms, it creates a matrix, and each of these columns is essentially corresponding to the polynomial. So x squared, x cubed, and x to the 4th. Okay. So if we take this and I create a prediction in order to plot it, I will predict over a range of x's across the range that we see in the plot. So run this, and see what happens in the summary. You actually get a whole bunch of terms, right? Now you have coefficients related to each of the x's, but it's kind of like when I was saying you lose some of the interpretability, right? In this case, you're basically saying, as x squared changes by 1 unit, the estimate changes by some amount. So it becomes very hard to think about like an individual level effect because it's the aggregate of all of these polynomial terms. Nevertheless, let's take a look at our plot if we include this polynomial. We can use this curve in order to plot it. So this would be the true function here compared to the linear. Let's see, it's saying that I have some kind of mistake. 1 second. Here. Same thing as before. Okay, so let's plot this again. And let me make the line width a little bit larger so it's easier to see. So that blue line represents the true value, and that's our linear regression. And let's take a look at what the prediction looks like for our polynomial. So instead of the AB line fit here, I'm going to add our predictions. So if this recall, this is what our true form looks like. The best our linear model could do was a straight line through all of this. And let's see what 25 polynomial terms adds. Okay, so a lot closer, right? If you think about um, the size of the error of your straight linear term, and how far it is from my dash blue line essentially compared to the red line, which definitely isn't perfect, right? We can see particularly kind of here in the middle area, you can see that it strays a little bit from the blues. It lines up pretty well at the end, but before that, not the best. And then, as I had mentioned before, sort of at the boundaries of our x terms, you might get some aberrant behavior, right? So that's what we're observing here, and that's due to the fact that the polynomials introduce a lot of this variation uh, at the boundaries. But overall, right, we can see that the red line is um, much better in this case than it is in the pure linear regression. And it's pretty nice that you can leverage something fairly simple and introduce actually quite a bit of complexity and ability to capture complexity into the model with simple polynomial terms. And so we're actually walking through sort of an evolution of models. And so what I'll say is that no one actually uses these polynomial terms in order to capture sort of nonlinearities. We're going to see sort of better examples of it in a moment that actually builds off of polynomial terms. Great. So let's move on and talk about the next nonlinear model. And so I'm going to jump back to the whiteboard. So the next regression we're going to look at is known as piecewise regression. This is also known as segmented regressions. So we'll have yi is equal to beta 0 plus beta 1 xi plus epsilon, our error term. And it's actually fairly straightforward. You break your regression into multiple pieces. And so might look something like this. Where BP is known as a breakpoint. So imagine that you have data that looks like this. And if you ran like a regular linear regression, maybe your results would look basically flat. But if I were to do two regressions, I could have a piecewise or segmented regression one going up to here, setting a breakpoint over here, and then another one down like this. And if you think about it, in fact, you could, in theory, segment your regression to do a line between every single point, which would then mean you're running segmented regression with a breakpoint at every single value of X in your data. So how many breakpoints should you have? Same answer as we think about a lot of these going in between extremes for adding flexibility into our models. You can do this through sort of cross-validation. Okay, and so this is, as you can see, a fairly different approach compared to the polynomial regression in order to add flexibility into our model. And let's take a look back at our original example and essentially see how well it does. So jumping back on over to our studio. Here, we're actually going to need a package called segmented. And we're going to create a piecewise model using the function segmented. And actually, you just input your linear model here. I'll talk about what these terms do in just a second, or what these inputs are. Okay, so we put in our linear model, and then the variable that we are segmenting is X, right? We are going to run multiple regressions at different intervals of X. And the breakpoints is provided by this term psi. And we're actually just going to run a breakpoint every 0.2. So every unit 1 is going to have 5 breakpoints. And we will use this to predict an outcome across our data. All right, so I run both of those. And let's copy and paste our plot here. Excuse me. Where we have our true line here, which is essentially what we are trying to calibrate to. And I'm going to replace my Y with my new predict. And let's just change the color. Actually, we'll leave it red for now. Okay, so here are our points. Here is the true line. And using our piecewise model, here is our regression. Okay, actually, we only went from 0.5 to 4.5, which is why this line at the end goes through all of this. Let me see what happens if we go all the way up to 5. There might be some issues like right at the border. Yeah, out of range. And that's probably because we're using this uniform regression, or we're drawing from a uniform distribution, and you might not have points going all the way out that far. but let's try something a little bit higher. Nope, still. Probably needs some number of data points there. See how low we can go. Okay, here we go. Let's try that again. Okay, great. So we can see here, slightly better at the end. And in this case, when I run a regression like this, comparing to our polynomial prediction, I would actually say that in the middle area here, and then where we were observing some larger errors over here, the piecewise might actually be doing a little bit better. Now it's not as good at getting those smooth curves, right? But other than that, it looks like it's closer on to the blue points. And in fact, we can compare these directly. If I add this line here, and I change the color. So let's go ahead and run all of these guys. And if I pull this out, so we can see it a little bit bigger. So the question is, who is closer to the blue line? Is it the red or the green line? And particularly here we can see, right, the green line tends to do a little bit better. So two different approaches, and both of these are substantially better than just doing a linear regression in terms of the fits. And these are fairly basic approaches that are already allowing us to introduce a lot more flexibility outside of a linear functional form. Okay. And what I'll say about the piecewise model is that similar to the polynomial, we don't actually use piecewise for any, serious analysis. Um, this is kind of for instructive purposes, right? We're walking through this evolution of getting to nonlinearity. And we are getting a little bit closer to techniques that are actually employed. And maybe you can guess that the sort of next step is actually the combination of the piecewise model and the polynomial model. And so that's the next thing that we will talk about. So jumping back to the whiteboard. We will now explore the concept of splines, which are essentially like piecewise polynomial functions. But there are some hidden details to consider. So let's look at an example here. Let's suppose we have some data that looks maybe something like this. And with what we'll think of as a piecewise cubic. This would be 2 cubic, right? So this would be a simple polynomial regression line segments. So we have a polynomial order 3 and a segmented regression with a single breakpoint. So let's make a breakpoint right here. And what ends up happening is something, let's say like this, and then let's do something like that. So in this case, what you'll find is that you have a discontinuity in your fit at the breakpoint, and that would be a common result of a piecewise cubic function. So let's try and add a constraint. So let me replicate this plot here. Okay. So I still have a breakpoint right here. And let's do something called a continuous piecewise cubic. And essentially what we'll do is we are going to take this right here, and we are going to add an additional constraint that the lines must touch. Okay, I'm not going to get into the math of this, but essentially what ends up happening is you might instead get something like this. And line happens like that. And actually, let me try and make my example a little bit more clear. Okay. So now the lines connect, but they are a non-smooth connection. So in other words, typically you're going to observe a kink at the breakpoint. So our last example, so we're going to add one more thing here. So additional, I can spell, hang on. Additional constraint that lines must be smooth at the breakpoint. Okay, I won't get into the math here again, but generally essentially what's happening is the first and second derivatives are continuous at the cutoff or breakpoint. Okay, so this looks something like this. And here we'll have some kind of smoothed out bit. And what's happening at the breakpoint here, this sort of smoothed out transition is known as a knot. Okay, so the knot contains information about, so the number of knots, right? You're going to have a knot at every breakpoint. And this final form is known as the spline. So this is a cubic spline because the polynomial terms is 3. And so actually one of the nice features of these splines is now I have flexibility in several directions, right? With the polynomials, I have some decision to make about how many polynomials to have. Um, and then with the piecewise regression, I have some decision to make about how many segments to have and how many breakpoints. In this case, like a lot of traditional splines are typically cubic. That introduces enough sort of flexibility that then the rest of the flexibility is determined by the number of knots that you include in the model. And the way this is termed, this looks something like this: beta 0 plus beta 1 b1 xi plus beta 2 b2 xi and so on. Beta k plus 3 b k plus 3 xi. That's my error term. And the betas are known as these basis functions that transform, the b's, sorry, not the betas. The b's are represent basis functions that are transforming the data in order to get that sort of fit. Okay, and so that contains information about the knots. So here, because you are transforming our inputs, then the betas are no longer easily interpretable with respect to original data. But as you'll see in a moment, and as you can probably imagine, the amount of flexibility afforded by these splines and its ability to fit highly nonlinear functions is one of the big benefits that you're making as a trade-off to lose this interpretability. So cubic splines are the most common. And we trade off the polynomial. In other words, having lots of xn terms for knots. So let's take a quick look. If I were to have lots of data points, trying to make these kind of similar. Zero knots, 1 knot, 2 knots. So with no knots, maybe my cubic looks something like this. Maybe with 1 knot, if I have like a breakpoint here, maybe it'll do something like that. Maybe if I have another knot, you get even more. Something like this. And so knots add flexibility to the model fit. Okay, and so if you can imagine the choice here, which is how many knots should I add? And the more knots that I'm adding, the more flexibility I'm introducing into the model. So same question that I've been posing for all of class. The determination of the number of knots can be decided by using a procedure to test our out of sample predictability. And so the number of knots can be determined by something like cross-validation. And so our sort of book ends, right? 0 knots up to the number of knots equal to your points, and somewhere in between there. With 0 knots, you're probably not having enough flexibility. With knots equal to the number of data points, you're probably overfitting. And so the sweet spot is probably somewhere in between. So the last piece that I will add to our discussion about cubic splines is actually getting to an area where people are actually employing these types of approaches, and that is known as sort of last step in our evolution from combining polynomial and stepwise, and then making things continuous, right, into a spline, and then thinking specifically about the cubic spline, which is the most common form um, of these polynomial splines, and then thinking about natural splines, which is basically a cubic spline, but we add one last thing. So splines can have high variance in outer range of predictors. This is the same phenomenon that I was talking about with polynomial regression. And if you remember back to the example that we were just plotting, right, the red line right at the beginning of the x's was like all over the place. And actually splines can still have this kind of artifact. And so what natural splines do, natural splines add constraints so that function is linear at boundaries. So if I plot this, just a whole bunch of points here. Okay, and if I were to plot something here, essentially what ends up happening is that when your cubic spline ends up something like this, the natural spline has these constraints that kind of tighten down the edges so that it's so that you're like tighter on the boundaries, especially at the boundaries of X. Okay, and so we're gonna take a look in R to observe basically how all of these we can run the cubic spline and then do a comparison with the natural spline functions. So jump on back over to R. Okay. So let's go ahead and build back up kind of in the same way as we discussed in the notes. So here I'm going to run not a spline, but first I'm going to run our cubic linear model, and then I'm going to do the segmented regression on that. So this is kind of like the first example. I have psi set to 2.5, so there is exactly one breakpoint halfway through. And we have to do a predict. And I'm going to reorder it just so that it runs from small x all the way up. Okay. So that is our cubic linear model. We do a segmented version of the cubic linear model, and then we predict based off of that model. Let's grab our old code here so that we have our starting point of the data plus the true fit of the line. And let's go ahead and add in our predicted. Okay. So here we have a breakpoint in the middle, and then the cubic, not adding a whole bunch. And it is slightly nonlinear, right? Especially when we think about in comparison to our line. And we actually noticed this artifact here where the line suddenly drops down. Again, that's due to the weird things that happen at the boundaries. But generally not great. Okay. And so let's go ahead and take the next step to actually make it so that there is a knot instead of a breakpoint in the cubic. And so really turning this into a proper spline. And we're going to use a library called splines to do this analysis. Okay, so cubic spline 1, and I'm going to run a linear regression. And I'm going to use a function called BS, which is the basis transformation function that I was talking about. And the knots are going to be located in step intervals of 1 from 0 to 5. And so we should have 1, 2, 3, 4, 4 breakpoints, and then the ones at the end. And we'll have our predict. Similar to what we've been doing before, running our X across the range of interest. So something like this. And I added a standard error equals true so that we can observe what happens in standard error, particularly at the bounds, and that'll be useful to see when we compare against the natural spline. And actually, what I would like to do here is to add in, so I've copy and pasted from my code, essentially exactly the same thing, but I'm running a couple models here. So cubic spline 1, 2, 3, 4. And the only difference between these is that the knots that are getting sequenced across the data are increasing in frequency. So here it's every 0.5, which means that I've essentially doubled the number of knots. Remember, I had 4 before, at 1, at 2, at 3, and 4. Now I have one at 0.5, at 1, at 1.5, at 2, and so on. So you should have twice as many knots in this one. Here, I'm doing it every 0.3, so you should have approximately 3 times as many. And then in the last one, we'll have every 0.1, which means I should have about 10 times as many knots as my first model. So I'm going to go ahead and run all of this. I do have some warnings again about things that are happening at the boundaries, but we're not going to worry about that. Okay. And let's see what happens. So I've copied and pasted some code here. It's going to be essentially the same as before. We're going to plot all of the lines, and then I'm going to plot the fits of these guys one at a time, and include the standard errors. So we'll walk through this slowly. So here's all the points. I'm graying them out a little bit so it's a little bit clearer because we're going to overlay quite a few lines here. That is the first fit, okay? And that is the fit when essentially when you're having a cubic spline with 4 breakpoints. And the error or the dashed lines around that indicate the confidence intervals of our mean fit values. Okay, here we are with twice as many knots. And you can see that as I increase the number of knots, the squiggliness of the line starts to increase. I have a little bit more flexibility. And that really starts at the ends. You can see, okay, now I'm kind of fitting the points a little bit more at the ends, both at the beginning and at the end. And let's really quickly just add these. Actually, I'm going to maybe for now leave these guys out. It's going to make the chart really busy, and we can revisit this when we look at the natural spline. So let me rerun this. Okay, that's 4 splines, 8 splines, or sorry, not splines, knots, and then let's see what happens here. Okay, all of a sudden, I'm hitting kind of a critical mass, right? It's still kind of not perfect. You can see the peaks aren't great in some areas, but wow, this is doing significantly better than when you have fewer knots. And let's go ahead and do it with this last one. And let me zoom in here so we can see. Yeah, so where we were having some of those deficiencies in the orange before, by introducing a larger number of knots, you were starting to get really close, right? Or a lot better than the previous ones. And in fact, if I were to jump back and grab the true curve, and let's just make this guy black and add that here. Yeah, you can see that our true line, which is the dashed black line, is, yeah, basically right on top of the green line the whole way down, right? You can see, okay, there's some imperfections in several areas, but for the most part, it's actually a really nice fit. And that model is not very complex. Like the only thing essentially that you've added is to increase the number of knots. Let's consider one step forward. And go crazy with the number of knots. Okay, so every 0.0025. So what is that? 5 divided by 0.0025. So we're gonna add 2,000 knots-ish, up from what, 50? And so think about what's gonna happen here. Okay. So in this case, actually, I thought it would be more squiggly than this. Let me see if this is right on the zoom. No, okay. Well, in this particular case, as I add substantially more knots, you are starting to fit closer and closer to the data. But of course, you can add a lot more. You can actually add more than there are a number of data points, and you might get these sort of warning messages when that happens. Okay, so now let us consider the natural spline. And this is actually substantially easier. They've kind of baked it into allow you to add simply degrees of freedom. And one of the convenient things about this is by specifying this kind of uses a procedure to help find the location of the knots for you. And we can predict using this model with 10 degrees of freedom, or about 10 knots. And I will use the same predict that I had from up here. And we can repeat this procedure in a similar fashion where I increase the number of degrees of freedom. And let's go ahead and plot this. Here I'm going to take out the standard errors just for now. We'll do a comparison of the standard errors in just a second. Okay, so if I run all of this code, which is running my natural spline regressions. Oh, uh-oh, what's happening here? Oh, I had too many. Okay. There is with 10 degrees of freedom. Here's with 15 degrees of freedom. And orange is with 30 degrees of freedom. And we can see, again, fairly simple models that allow us to get really nail down fairly complex functional forms that are not linear. And let's see what happens. I'm going to look at the comparison between my cubic splines and my natural splines. And this time, what I'm going to do is include my standard errors. And so we're going to look at our best model from the cubic splines, including the standard error. And we are going to look at the best prediction from our natural splines, which is this orange one, which has 30 degrees of freedom. And when I compare the two, you can see that in comparison to, what is this black line here? Okay, the black line is our true value. So actually, is that right? It doesn't seem, for some reason, hang on. For some reason, the black line has straight lines, it looks like. It's because it's an approximation based off of the actual x values, but you can imagine if it's smoothed out, kind of what it would look like. Okay, but generally speaking, if I look at my red and blue lines and compare them to the black lines, they're basically all kind of on top of each other. There's like, I guess right here in the middle, there's an area that's kind of hard to capture properly. There's kind of a lot going on with the how it transitions here. And so, yeah, we're actually not doing as well just right at this point, but everywhere else, basically, we're sort of right on par. And the thing to keep in mind in our comparison of our natural versus our cubic spline is sort of right at the end here. You can see the standard error starts to do some wonky stuff. The blue cubic line curves a little bit more right at the boundaries, whereas our red natural spline is pretty smoothed out over here. And that's a result of like specific constraints that keep it from doing the sort of high variation high variation fit right at the boundaries. Okay. Now let's see one more thing. I'm going to run one last model, natural spline 4. And this time I'm going to have 10 times as many degrees of freedom, so 300 degrees of freedom. I'm going to run all of this through. And let's see what happens and what this plot looks like. Okay. So in comparison to some of the previous fits, here you can see that these lines are actually trying to fit like individual jitter between each of the data points, right? And so you have a line that's like way more squiggly. Knowing all that we know about the true function, you could look at this and say, well, this is like overfit, right? And so that is the idea here, is that as you increase the number of knots or the degrees of freedom, um, you will start to pass our sweet spot of lowering our total error for out of sample prediction, and you'll start to get into this territory where we're kind of obviously overfitting the model. And so to jump back to that sort of core concept from class, the way that we want to properly select the number of degrees of freedom is to use cross-validation to determine how much flexibility that we actually want in our model. And so we would avoid some, in order to avoid something like this. Okay. So natural splines are a technique that is commonly used. And this is a great way to kind of very easily be able to fit a highly non-linear set of data. And we're going to talk about one more type of smoothing, or one more type of spline um, that's known as a smoothing spline, which is it's going to kind of build on the concepts that we talked about with ridge and lasso regression as kind of a novel way of um, approaching this sort of class of models. So I'm going to go ahead and jump back on over to my whiteboard. And we're going to talk about smoothing splines. So when I think about the type of models that I was just describing, we have something that looks like this. And this may look fairly familiar when we compare it to linear regression, but there's kind of one noticeable difference, which is this term here. Instead of just our y hat, this is considering the basis transformation of our x inputs, right? And so where gxi is the spline cubic function that constrains the first and second derivatives to be continuous. And let's actually think about this last concept that we were just looking over, which I was saying is like a bad thing. So suppose you had a knot for every point. So that would result ostensibly in a plot that might look something like this. Maybe I've got Some kind of crazy fit, right? And as we've kind of discussed, this will perfectly minimize RSS, but you have overfitting. So remember the concept in the lasso and ridge regression, very similar to this, where we introduce into the model additional terms to add flexibility, right? So it's almost analogous. I have lots of variables, and I am thinking about ways to strategic ways of including those variables to balance out kind of getting the best model possible without overfitting. In the ridge and lasso regression, what did we do? We took all of those variables that we had and we threw them into the model. And the ridge and lasso regression had these penalty functions that would say, hey, I'm going to make the like contribution of certain variables smaller in order to avoid overfitting. So we can do something similar here. Let's, in the same way that the ridge and lasso say, throw in all the variables, here we're going to say, put in a knot for every data point. And what we're going to do is shrink the second derivative. So consider our equation that we just went through. And now I'm going to add a penalty function. And that lambda is our sort of familiar tuning parameter. And this whole thing here is our penalty function. Okay, so like a ridge regression, this penalizes the function by encouraging smoothness. So rate of change of slope should not be too big. So think about what this is saying here. Let's do a comparison of two models with different tuning parameter values. So with a low lambda, so if my lambda is equal to 0, then this term here goes away, and you are free to use all of those knots and go crazy wild, right? And so this function will do something like that. And if you have a high lambda, maybe essentially what happens is that the second derivative term, right, which is what allows your line to get sort of really squiggly, it's saying, well, the larger that term is, or in other words, the more you're allowed to rapidly change directions in your line, um, the larger your penalty ends up being. And so there's this balance that happens between, yeah, I have lots of flexibility with my knots, but I have to make my line really smooth, or in other words, I can't make it change. I can't make the line change direction very quickly. And so you end up getting a smoothed out line that looks something like this. How do I decide whether to choose this low lambda or this high lambda? All right, say it with me again, cross validation. And so let's take a look at our example that we've been using in class and employ this smoothing spline and see how this compares to some of our previous examples. And the really nice thing about this kind of approach is that now you have reduced the kind of work that you need to do in terms of like finding out the number of knots and placing them in the right places in our cubic spline, or figuring out the degrees of freedom. It's all boiled down to this one tuning parameter, and that's all you need to calibrate. Okay, so I'm just going to copy and paste it here. We use a function called smooth.spline. The inputs are a little bit different. You set this up with your X inputs and your Y inputs like so. And this SPAR represents the tuning parameter value that you want to take. And so again, the larger the tuning parameter, the less the line is able to change direction, and the smaller the tuning parameter, then you're more able to take advantage of all of those knots to make your line go all over the place. So let's take a look at what these look like. So our starting point here, again, with all of our points. Okay, so here's the most penalized line. Great. And so as you can imagine, high penalty, it's basically saying, hey, wait, you can't go up and down a lot with your line. So the closer or the larger this penalty function is, the closer you're going to start looking more like just a straight line, right? And with a totally straight line, your second derivative is actually just equal to 0, right? And so it's reducing that penalty function, the value of the penalty term down to 0 by having your line be as flat as possible. Okay, and so we start easing off of that tuning parameter. We go from 1 to 0.75, which says, hey, you're allowed to start changing the direction of your line a little bit more in that second derivative. And you can see we're starting to get some of that squiggliness. And there is a tuning parameter 0.5, orange at 0.25, and then with 0, you can have sort of as many knots as you want, and you end up with something that we might consider slightly overfit, right? And so that black line is starting to squiggle a lot more, and actually you can even start to see that in the orange line with the tuning parameter set to 0.25, and maybe green is our best one. Okay, and so as I was mentioning, your tuning parameter should be set via a cross-validation procedure, but luckily, um, we're not gonna go into that function, that sort of customized k-fold cross-validation function that I made, right? These are built into the properties of a lot of these functions that employ them. And so to run our smooth spline model, we can do something like this. X equals X, Y equals Y, and then instead of setting the tuning parameter, I say CV equals true. So it's going to figure out what the best tuning parameter is using a cross-validation procedure, which we enable by having CV equals true. And I go ahead and run this, and I should be able to see how this compares against our true function in red. And here, finally, there is our smooth spline function compared to our true function. And you can see it's pretty darn close, okay? And just, take a second to imagine kind of the complexity that you would need to emulate this data using some linear regression form, right? Like something with this many sort of curves is going to require quite a bit of degrees of freedom in order to sort of accurately capture the functional form. Whereas with the spline, a very simple approach, right? Integrating all of this stuff that we've talked about, going from polynomial, combining it with segmented, doing the spline procedure to make sure that they're continuous at the knots, and then finally allowing the spline to do as many knots as it wants, and then adding this penalty function to the ability of a line to smooth out. And that gets wrapped up into this fairly simple function here, and it allows us to do this very sort of complex fit with a high degree of precision and accuracy. So the spline here is a sort of very powerful tool that lets us get at these nonlinear terms. Okay, since we still have a little bit of time here, I'm going to continue on with one last piece. Okay, so jumping back to the whiteboard, there is a sort of hybrid approach between our linear models and our splines where we want to try and maintain some of the interpretability of the data, but take advantage of some of the power of the splines, and actually specifically the smoothing spline, which is the last spline that we talked about. And so there's this class of models known as generalized additive models, or also known as a GAM. So this maintains some interpretability by additivity of terms. So it uses splines for each individual variable and then adds them together. So we go from something like yi equals beta naught plus beta 1 xi1 plus beta 2 xi2, so on and so forth. And we transform this into this, which is our smoothing function. But notice we have a j number of smoothing functions where j is the index for each individual variable. And I think the sort of easiest way to interpret this is to look at an example in R. Okay, so we'll jump back over. We're going to use some real data. And so this is data from the hitters data set, which is that baseball data set that we had used before when we were doing variable selection. That comes from the ISLR library, which we've used before, and we need to use the MGCV package, which is what allows us to run general additive models. Okay, so let's look at a model here, which I'll already put together. And let's take a look at this summary. Okay, and so we have our typical coefficient estimates. And you guys should all be able to interpret how these work at this point. We can see they're all statistically significant and sort of contributing to our ability to capture the variation in this model. And let's look at GAM fit, which is now going to use this GAM function to fit our model. And the way this works is that we individually smooth out variables, and you do that with this S function. And so I can do something like this. Say I want smooth splines to be describing these variables. And so this is going to prevent us from having like an interpretable coefficient like we have in our linear model. But it's going to allow us to individually apply splines to the data. And we're going to see why that's useful in just a second. The other thing that I'll note is that I haven't smoothed out all the variables, and that's not a typo. So CRBI, the division, and putouts, um, these are all left in the regular form without the smoothing spline. And that's one of the nice things with the GAM function and with general additive models in general is that I can maintain like a linear functional form for specific variables, and these will actually have corresponding betas that I can interpret in the exact same way as before. So let's go ahead and take a look at the summary of our GAM fit. Okay, and so here we've got linear estimates with coefficients that are actually going to be pretty close to before, I believe. So CRBI is 0.658. Here it's 0.527. Division W, -122, -123, and putouts 0.209. Up here, 275. So relatively close. So that is being applied to the ones where we didn't smooth them out and they remain as these linear terms. And then we've got this like smoothed out terms over here, which these are metrics that aren't really going to give you any interpretability in terms of how the shape of the fit changes across ranges of each of these variables. But they do have some diagnostic things about like statistical significance as it relates to an interpretation somewhat similar to these guys. And it's essentially, okay, how different are these from zero? But here we can do something neat. If I plot this in our typical plotting function, include the standard errors, and then there's this extra option that I have pages equals 1, because actually this prints out, this is actually going to plot out a whole bunch of different plots, and I'm just sticking them all into one page. Okay, so let's zoom here and look at this. Okay, what the heck are we looking at? So this is a visual representation of the individual fits as it relates to my outcome variable. Okay, so what does that mean? So to pay extra attention here, I found this is like one area that has caused some confusion amongst students in the past. So if I were to do this plot for the 3 variables that I'd left out, CRBI, division, and putouts, what you would see is a straight line. Okay. And the information of that straight line is entirely being provided in the beta, right? That's just the slope. Okay, so it's basically saying as the one of those individual variables changes, how much does my Y change? Or in other words, how much in this particular model, we're looking at player salaries. So as I change RBI or CRBI, the division or putouts, how much does my Y, my salary change? In this case, for a non-linear specification, where we're using splines, you can't describe that in one number anymore, but you can show it in a plot. And in fact, that's exactly what this stuff is showing, is the change in salary across the number of at-bats, across the number of hits, across the number of walks, and so on, right? So, you know, the more often you hit the ball, generally, the higher your salary is on average. The more walks you have, the higher your salary is on average, and it changes in this shape. And they're no longer linear. So you could say something like, okay, at the beginning, if you have some number of walks, your salary doesn't change that much up until you get to some threshold of like 50 walks, and then it starts to increase substantially more for the number of walks that you're giving. That would kind of be the interpretation here. So really, the graphs here are displaying kind of like what the betas are telling you. It's telling you the relationship between that individual x variable and my outcome. So x on the x-axis, y on the y-axis. And you can see the nonlinear trend in the patterns. And then the standard error is kind of being described by the dotted line. There are these little black lines at the bottom of the plot along the x-axis. Those lines represent the actual data points in the data sets. And so that gives you a sense of the range of data that you see, but it also tells you kind of where I guess the outliers in some sense would be. So in C runs, for example, like the vast majority of data is like lower than 500. And so really, if you were to cover up everything past 500, that would give you kind of the trend for most of the data. And then because there's so sparse amount of data out here towards the right-hand side of the plot, the errors kind of grow a lot more or become much larger in comparison. Yeah, so this is a really handy visualization tool that allows you to visualize whether relationships between your explanatory variables and your response variable is linear. If you are just running these linear models, one of the things that I will always encourage is just run it through a GAM, add the splines, and see, how good is your assumption that the functional form is linear, right? So, if the plot were to look kind of like walks, I might say, okay, that seems like fairly reasonable to be a linear fit. But if you are, let's say, C runs or app where you're seeing these kind of like inflection points, some like a positive slope to a negative slope, I might say, well, your assumption about linearity and then thus the application of a linear regression is probably no longer appropriate. And you can run this for any linear model that you're doing. And I could add in my smoothing spline to any continuous variable. You can't actually do it for categorical variables, which is probably why it's left off of division. But if I added splines to these two guys and then plotted it again, one of the things that you would see is, so CRBI, which I had left out, and putouts, which I had left out, these are both fairly linear. And so what I had done originally in sort of diagnosing this model and figuring out what to do, you just check it with the smoothing splines. And if it looks fairly straight, right, fairly linear, you say, okay, well, that's linearity is probably a safe assumption. And so I'm just gonna go ahead and get rid of those smoothing splines. And I do that because I now have better interpretability by having my beta, but I'm not actually sacrificing anything in the fit because I can kind of tell that they're fairly straight lines, right? And I've left the smoothing splines on the rest of the variables, kind of given that they are not quite as straight lines as the other two. So this really should be kind of a default starting point when you're putting together a linear regression model, just to make sure that the functional form that you're trying to fit against is actually linear. Because if it's not, yeah, you're probably adding some kind of bias into your model, or you're going to have a larger error than you necessarily need to. Um, and yeah, so this even if you are not employing this as kind of like a final run through model, it can be a nice diagnostic tool to verify that what you're doing is correct. Okay, and so that kind of wraps up our sort of full evolution of nonlinear models that are thinking specifically about splines for today. We will get to a couple other nonlinear approaches that are um, sort of very, very different in the way that they approach the fit. Um, but hopefully today you can see kind of the progression of complexity as we go from these simple polynomial and segmented regressions into slightly more complex, but hopefully logical models that are, yeah, still being used today for a number of things. And even thinking about the sort of hybrid in between with this general additive model that lets us kind of get a little bit in terms of the best of both worlds. Okay, and so that's it for today. And the next lecture will be online as well. So I will hopefully see you guys, yeah, in two lectures in person.